Hi, this is the second part in a series where I'm talking about steady state errors. We went ahead to talk about steady state errors in general, and we mentioned in the last video that the transient response is important, stability is important, but steady state error is also important. And before we find the steady state error, before we talk about steady state error, the system has to be stable. So after talking about stability, then we can talk about steady state error. So a system must be stable, and after we know it is stable, then we can compute the steady state error. Then we had a number of examples that went through. Please go through the previous video because I will not recap all of that right now. We found the steady state error for a number of different inputs. Specifically, we had the steady state error for a step input. I'll simply call that E step. So steady state error for a step input. And that turned out to be 1 over 1 plus the limit as s tends towards 0 of g of s. This was a steady state error for a step input. For a ramp input, E ramp was given as 1 over the limit as s tends towards 0 of s g of s. And we had the steady state error for a parabolic input. And that was 1 over the limit as s tends towards 0 of s squared g of s. So when we have these three parameters, because we have this limit term and co, it makes it a lot easier to just represent, to simply have this limit as represent this limit by a certain variable. So we have some certain variables that we use regularly, and there's a kp, something we just call a kp, and we define that as the limit as s tends towards 0 of g of s. We call this the position constant. Okay, we call this the position constant. Then we have another variable that we call kv that we define as the limit as s tends towards 0 of s g of s. This is called the velocity constant. So this is position constant, this is the velocity constant. Now, if you take a look at this, if this is position, differentiate it once, you get velocity. So we have s g of s. So if you want, you could think of it that way. And then you have your ka, which is your acceleration constant, which is given defined as the limit as s tends towards 0 of s squared g of s. So position constant, velocity constant, acceleration constant. But that means that we can now represent this step, the steady state error for a step input, that can now simply be represented as 1 over 1 plus kp, which is a very simple thing to write, a very simple expression to write. Let me write the p very well. And then E for a ramp input. So steady state error given a ramp input will be given as 1 over kv. And a steady state error for a parabola or parabolic input will be equal to 1 over ka. So we can write our steady state error using this equation or this equation on the other hand. This is called position constant, velocity constant, acceleration constant. Now, having said all of that, remember that we have types of systems, type 0, type 1, and type 2 systems. Now we want to somewhat formalize our discussion about types of systems and how we can get our steady state error if we know the type of a system. So here I'll draw a table. It's always easiest to represent this as a table. Firstly, in the first column in the table, I'll talk about the inputs. So because again, we generally define steady state errors in terms of the inputs. The first is for a step input, which is u of t. The second is for a ramp input, t u of t. And the third is for a parabolic input. Well, I should make this half so that this becomes a unit parabolic input. So when we have this, then we can get our steady state error. I'll just simply call this ESS. Steady state error, like we just wrote, I'll have this as 1 over 1 plus Kp, 1 over Kv, and 1 over Ka. So that would be our steady state error. Now, let's talk about different types of systems. If we have a type 0 system, then your Kp will be constant. Okay, Kp will be constant, your Kv will be equal to 0, and your Ka will be equal to 0. We could come back to the example we had just now. If we have a type 0 system, say this is a type 0 system, Kp is the limit as s tends to 0 of g of s. If this is our g of s, when s tends to 0, we end up with a constant. No matter what happens, this will definitely end up as a constant. Same thing here, this will definitely end up as a constant. It will not be 0, it will not be infinite. It will be 0, it will be a constant value. It could be a constant value in each of these two cases. So that's what we see for type 0 systems. On the other hand, if we were to find Kv for this system, Kv is the limit as s tends to 0 of s multiplied by g of s. So s multiplied by this, we'll put an s in the numerator. Once you make that s 0, no matter what's in the denominator, well, the denominator is not 0. So once you have that s in the numerator, this will be 0. Same thing here, s multiplied by this entire numerator will give us 0. So for Kv will be 0 if it is a type 0 system. If your Ka, to find your Ka, again, your Ka, like we have it down here, Ka is the limit as s tends to 0 of s squared g of s. You can put that here, multiply the numerator by s squared. There is no s in the denominator to cancel that out. So you're left with 0. Okay, so for type 0 system, your Kv will be 0, your Ka will be 0, your Kp will be a constant, a non-zero constant, and a finite number. So given that, it means that your steady state error, if we now want to talk about the steady state error for a type 0 system, okay, sorry, I put that, let me, so I'll put this here, ESS. So I want all of this to be under type 0. And if you want, we could call this the static error constants here, okay? So the static error constants. So that's what's in this column. So your Kp, Kv, and K are the static error constants: position error, velocity error, and acceleration error. Now your steady state error will be 1 over 1 plus Kp. I've not done anything new. That's exactly what we had over here. But for your position error, sorry, for your velocity, for a type 1 system, let's say your input were a ramp input, your steady state error will be 1 over 0, which will give us infinity. For a ramp input, for a parabolic input, again, your steady state error will be 1 over 0, which will be infinity. So if we have a type 0 system and you supply a ramp input or a parabolic input, you are guaranteed to have an infinite steady state error. Let's see if we can put that into practice or simulate that. So what I'm doing here is I have a Simulink model that I've created. This is the Simulink model. I supply a ramp here, integrate it twice. First time you integrate a step, you get a ramp. Next time you integrate first time you integrate a ramp, you get a parabola. So I'm sending this, and each of them is going into this subsystem. This subsystem is exactly the same thing. Now, this is defined by ZPK, and I just simply call them Z, P, and K, so that in MATLAB, I can assign values to Z, P, and K. Okay, I have a unity feedback system like we're dealing with. Now, this is the same thing I duplicated for all these cases. I just duplicated the subsystem in 3 places. So I'm sending this input. So I'm sending a step into the first, a ramp into the second, a parabola into the third. I'm taking out the step response, the ramp response, and the parabola response, and I have that in here docked in MATLAB so that I can just go ahead and run everything from here. I'll simulate the Simulink the Simulink model from within the MATLAB window. First system I'm dealing with, I'm just simply going to use no 0, okay? No 0, and I'll use a gain of 1 because, well, that's convenient to use. So in a case where I have just one pole, okay, one pole, and the pole is not at the origin. Remember, the type of the system is dependent by the number of poles at the origin, okay? So there is no pole at the origin. So I have just one pole and none at the origin. When I go ahead and run that, that's actually what's showing up at present, but let me go ahead and run that again. So once I run that, we see the response over here. So we said that for this is a type 0 system. For a type 0 system, okay, let's have that here. For a type 0 system, we expect a constant steady state error, which will be 1 over 1 plus Kp, whatever Kp is, okay? Kp we can find, but Kp will be a constant. It could be an actual number. So when we have that, we have a constant steady state error. We see that once the system's response has settled down, you have a constant steady state error. Here it is constant. If we go to the ramp response, on the other hand, we expect an infinite steady state error to a ramp input. Ramp response, that's what you see. You see there are divergent lines. Okay, the output is divergent from the input. That suggests that as you keep on going, you end up with an infinite steady state error. In fact, it just keeps on diverging. So you will not have your steady state error as time goes towards infinity will get to infinity. For a parabolic response, you also expect the same thing. And here you see two lines that are diverging. Okay, they are divergent, so it means you have an infinite steady state error. Let's look at a type 1 system instead. If we had a type 1 system, for a type 1 system, our static error constants are here. I'll just call them SEC, and then we'll have our ESS, steady state error, on that side. The static, so for your KP will be infinite for a type 1 system. For a type 1 system, your KP will be infinite. Your KV, on the other hand, will be constant, and your KA will be 0. We could take a look at, again, these examples we had over here to find out if that's the case. Now a type 1 system. Type 1 system, to find your KP is down here. KP is the limit as S tends towards 0 of G. So limit as S tends towards 0 of this term. As S tends towards 0 of this, you simply have your denominator going to 0. So you have 3 over 0, which is infinity. So your KP will definitely be infinite. Come over here as well. You get exactly the same thing. KP is infinite. And that's what we have in the table. KP is infinite. On the other hand, your KV is the limit as S tends towards 0 of S multiplied by G of S. For a type 1 system, we are multiplying the numerator by S. S will cancel out what the S in the denominator, so you're left with, by the time you find the limit, you end up with a constant. Same thing with this example, you end up with a constant. And you can take a look at your KA, you find out that your KA will always be 0, okay, for a type 1 system. So that means that if your KP is infinite, then your steady state error, 1 over 1 plus KP, will be 1 over 1 plus infinity, which will be 1 over infinity, which will be equal to 0. So for a type 1 system, you will definitely have 0 as your steady state error. Your steady state error to a ramp input will be 1 over KV, because your KV is a constant, so it could be 1 over KV, and your steady state error, if you had a parabolic input, will be 1 over 0, which is infinity. Okay, 1 over 0, which is infinity. So in other words, you have an infinite steady state error if you had a type 1 system and you supply it with a ramp input. I'll just go ahead and finish this table for a type 2 system. For a type 2 system, you have your SEC, static error constant, and your ESS. So your static error constant, your KP will be equal to infinity. You can check this out. Your KV will also be equal to infinity, and your KA will be constant. So your steady state error will be 0, 0, and in this case, 1 over KA. Let's go ahead and check MATLAB. Let's define MATLAB examples and let's see if we could do that. So I'll pick a different case now. To make a type 1 system, I'm going to place a pole at the origin. So one pole is at 0, another pole is at -1. When I go ahead and run that, so want to see our step response, I'll go ahead and run this. Press enter. And it has run. Now you see that your step response settles to exactly the same level as the input. 0 steady state error. Okay? 0 steady state error. Come to our ramp response. Now you see your ramp is exactly parallel. Your output response is exactly parallel to your ramp input. That gives us a constant steady state error. Remember, this is a type 1 system. Constant steady state error. For your parabola, on the other hand, it is diverging. Okay, it is divergent, so it is getting, the gap between them is getting wider. That means it could go to infinity as time goes to infinity. Let's define a second, let's simulate a type 2 system. So I'll place 2 poles at the origin, and then I leave the other pole at -1. By the way, let me put more poles in there just to show that it doesn't have to just be one other pole. We can have several other poles in there. Let's go ahead and run this simulation. I want to first see what the step response will be. So I go ahead and run this, and in a moment, okay, so I will need to increase the simulation time. Let's go to and let me increase the simulation time. If it might take a while to settle, then make this 100, and I'll go ahead and run this from within Simulink. I want to see what the response looks like. Okay, so this is something that we see here. What I have done is I've created an unstable system. I've now created an unstable system, and so there's no point in determining the steady state error. Okay, so let's try to rein this in. Okay, so here we go. Now we have a system that this is a type 2 system, 2 poles at the origin, and we see that for the step response, we have 0 steady state error. As time heads towards infinity, steady state error completely dies out. Taking a look at the ramp response, you see also you have 0 steady state error. At this initial stage, there's some overshoot and some perturbations about the final value, but then it settles down and you see there is 0 steady state error. But we take a look at the parabolic input on the other hand. Now this, you can almost see, okay, well, you can't quite see it right now. So let me, I may have to undock this. So let's see, can I zoom in directly into this? No, I can't. So I may have to undock this to ensure that we can view so I want to zoom into this just to show that, I just want to show that they are not exactly the same value, but they're actually parallel to each other. So now as we zoom in and zoom in, you see that they are exactly parallel to each other, which shows that you have a constant steady state error. It is not 0, but it is constant. So you have a constant steady state error for a parabolic input. To show that it was not that we didn't have a steady state error for the ramp inputs, I'm just going to come in here and zoom into that. Okay, so I'm just zooming into that so that you could see that there was actually a 0 steady state error in here. So this is 0 steady state error. The more I go, the more you can see that actually there are some perturbations and it is coming to settle at this final value. But the point is that you are ending up with the 0 steady state error. We could do the same thing for the step response. Well, step response, I think that's very clear that there is a 0 steady state error. So just by knowing the type of a system, you can determine whether or not you will have 0 steady state error depending on the inputs that you do receive. And in that case, you won't always have to do a calculation. Say you have a type 2 system and the input is a ramp input. You know the steady state error is going to be 0. You do not need to do a calculation for that. That will be it for this video. In the next video, next video will be the last one. In that video, what we will do is just take a simple example. Just take an example or two on steady state errors. Thank you.